Exercise 2230 is asking us to do retrosynthesis. They're giving us molecules and asking us to make them. And they do give us a hint. They say, how would you make these molecules using a Claisen condensation? And if they didn't say that, the features of the molecule that would give it away is that you have an ester, and on the beta position, you have a ketone. So you have a beta keto ester. That's always the product you get from a Claisen condensation. You get a beta keto ester. Now, in these Claisen condensations, you make them from two different esters coming together. And really, a leaving group on one of the esters was replaced by the nucleophilic alpha carbon of the second one. In other words, this bond here between the alpha carbon and the carbonyl carbon, that used to be an ester there. This is the bond that was made. So if you're trying to go backwards, break that bond. Cut it in half and draw the two pieces separately. So you break the bond between the alpha and beta carbons and draw the two pieces separately. So this is our sort of piece on the left, and this is our piece on the right. Now, when this alpha carbon attacked, as we saw in the video on the mechanism for this, it replaces the ester of this other molecule. So you just want to redraw the ether of the ester back in. You can make it match the other one, so you'd have, in this case, an ethoxy group. Now you'll notice that these two esters are not the same, and so we can't treat this just with a regular base. We wouldn't be able to treat this with sodium ethoxide because these esters are not the same. If the esters are ever not the same, the best procedure to do is to use LDA. And we've seen this before. We saw this and discussed this a little bit when we first introduced the crossed aldol products. We drew LDA. We said LDA is an acronym for lithium diisopropylamide, and the amide is referring to this nitrogen with a full negative charge. You have two isopropyl groups on there. That makes this very bulky, and the negative charge on the nitrogen is stabilized by a lithium, so lithium diisopropylamide. This is a really, really strong base, and what's crucial here is that this is a strong, bulky base. This will rip off an alpha hydrogen, only act as a base. It won't act as a nucleophile because it's so bulky. It will rip off the alpha hydrogen irreversibly. So you end up getting better yields with that. So here you could take the molecule that has the alpha hydrogen on it, this one. You would first treat that in one step with LDA, lithium diisopropylamide. That will turn this alpha position on every single one of those molecules into a nucleophile. Then, so that's our first molecule. Then you would take the second molecule and drip that into the reaction vessel. And as it drips in, this nucleophile will attack the carbonyl there and do the nucleophilic acyl substitution. And then at the end, you would want to do an acid wash to do proton transfers, but also remember to keep that relatively cool, because if it's warm, it will hydrolyze the ester. Okay, so much for lithium diisopropylamide. We discussed that in that previous video, so I just wanted to mention it quickly here. But anytime you try to do this Claisen condensation with two different esters, make sure you do LDA and do the stepwise reaction. Okay, let's think about this next one. We have an ester, we have the alpha carbon, and on the beta carbon we have a ketone. So we have a beta keto ester. That's the signature of a Claisen condensation. That's sort of a Claisen condensation writing on the molecule. Claisen condensation was here. So to draw the two esters you would need to make this, break the bond between the alpha and beta carbons and draw the two pieces of the molecule on each side of that separately. So on the left side, we'll have this molecule, On the right side, I'll have this one. So this molecule on the left is like this here, and then the molecule on the other side is like that there. Now these, with the Claisen condensation, these both start as esters. So take the molecule that has just the carbonyl and turn that into an ester. Add the same leaving group that the other molecule has. So here, an ethoxy group. Okay, so those are your two esters. Now you'll notice that these are not the same molecule, and so you'll want to use LDA. So if you take one of these, and since they both have alpha carbons, you can use either. Treat it with LDA. That will convert, let's say, this first molecule completely into alpha carbons that are nucleophiles. For the second step, drip your second ester into the molecule. As it drips in, these alpha carbons will attack the carbonyl there and do the nucleophilic acyl substitution. And last, do an acid wash. Make sure to do that at a relatively low temperature so you don't hydrolyze that ester. Okay, let's try C. Now the COOMe is really an ester. I'm going to redraw that to show you what it looks like in a skeletal structure. So if you compare the molecule on your homework with that, that's the COOMe that they have there. And if you look at this, you'll notice that what we are given is we have an ester, and we have an alpha carbon, and on the beta carbon we have a ketone. So we have a beta keto ester. And that is the signature sign that you did a Claisen condensation. You can make this from a Claisen condensation. So for a Claisen condensation, you want two esters. We can get those two esters by breaking the bond between the alpha and beta carbons. We're going to draw each of those pieces separately. So on the left, we have this group here, and on the right, we have this other group here. So, just to visually organize those, those are our two pieces there. So we broke the bond between the alpha and beta carbons. Now, in the Claisen condensation, both of these have to be esters. So the one that is not, just add the ester in. Use the same ether or alkoxy group as you have in the other ester, so OMe here. Now these are different esters, and anytime you have different esters, the most efficient reaction is going to be using LDA. So first use LDA. Doesn't matter in this case with which specific molecule. I'm going to use this blue one. That will turn the alpha carbon into a nucleophile on every single one of those molecules. It's irreversible, this LDA. Steals the hydrogen, does not give it back up. Then, in the second step, you would want to use your other ester. This alpha carbon nucleophile will attack the carbonyl carbon there. And then you just do an acid wash and make sure to do it at a relatively low temperature so that you don't hydrolyze the ester that you have there. And that's what you would need in order to create this beta keto ester. Okay, let's try another one. So I'm going to replace this COOMe with the skeletal structure for that. Anytime you see a COO and then anything other than an H, it means you've got an ester there. COOH is a carboxylic acid. So we'll have this COOMe. All right, now if you look at this, you'll notice that you have an ester, and not alpha to it, but on the beta carbon you have a ketone. So it's a beta keto ester. That is the sign that you've done a Claisen condensation. Now, to do a Claisen condensation, you need two esters that's condensed together, and to find out what those are, break the bond between the alpha and beta carbons. Redraw each of those pieces separately. So you could have the group on the left, and then the group on the right. And actually, make that just a little bit neater. Okay, so those are our two sort of carbon chains here. Now, you need two esters. One of them is already an ester. The other one needs to be add an alkoxy group. Add the same alkoxy group that's in the other ester. And these are our two esters. So you can see this group on the right visually is the same as this, and the group on the left is the same as this. We just added that OME in. So because these are two different esters, the base you want to use that will give you the most efficient product will be LDA. Once you use LDA, that will turn the alpha carbon, and you would want to start with this one because that's the one that has that alpha carbon with a hydrogen that can be ripped off. That'll turn that alpha carbon into a nucleophile in every single one of these molecules. Then take your second ester, drip that into your enolate solution. The alpha carbons will all attack the carbonyls and create this alpha-beta bond. And then you just do an acid wash. Just be careful to do it at a low temperature so you don't hydrolyze the ester that's left. So if you poured all of that into a boiling cauldron in those steps, you would get this beautiful, magnificent beta-keto ester out. Okay, so last one. If you look at this molecule, you will see an ester, and actually a very special type of ester. You'll see a cyclic ester. So the alkoxy group wraps around and is part of the same carbon chain as the carbonyl group. And that is specifically called a lactone. You might remember that when we had a nitrogen doing this in an amide, when we had an amide doing the same thing, that was called a lactam amide. Lactam, that's really important for antibiotics. You have beta-lactam antibiotics. A lactone is where you have that same feature but with an ester instead of an amide. So a cyclic ester is a lactone. And it's very common in essential oils of different plants, flowers, and other plants. And sometimes can be used as an antiseptic agent. So those lactones are interesting. We have that lactone here, not on the alpha carbon, but on the beta carbon we have a ketone. So we have a beta-keto ester, and that is the signature of a Claisen condensation. Now, to do a Claisen condensation, you need two esters. To figure out what those esters are, break the bond between the alpha and beta carbons, and redraw each of those pieces separately. So to the left of that bond, we would have this molecule. To the right of the bond, we would have this lactone. So just to organize that visually. Now, to do the Claisen condensation, you need two esters, so we just want to turn this other ester into an ester. An ester. We can't make the ester the same group as this one over here. So we can add just a small group. I'm going to add a methoxy group. Ultimately, this is going to be a leaving group, and it will be sort of a waste product that's floating around the solution by the end of the reaction. The reason why we've been using the same one in previous exercises is just so that the waste products we have don't become excessively complicated or unnecessarily complicated. So now that we have these two esters, they're different. Anytime the two esters are different, the most efficient thing you can do is to use LDA, lithium diisopropylamide, that really strong, very bulky base that will irreversibly steal the alpha hydrogens on the lactone and turn that alpha hydrogen, every molecule of that lactone, into a nucleophile. Once you have that nucleophile ready, once you have that sort of locked and loaded, you can drip your second ester into that solution, and every time it drips, the thousands of trillions of molecules in the one drop will be attacked by thousands of trillions of alpha carbons, and you'll create thousands of trillions of those alpha-beta bonds. And then you do an acid wash. Make sure you do it at a relatively low temperature so you don't hydrolyze this lactone, that ester that you have at the end. So if you mix all these things together in that order, you'll end up getting this really interesting beta-keto ester in your beaker. So, hopefully, this video gave you some practice, built some confidence with how you can create these beta-keto esters they're called crossed Claisen condensations because the two esters are different by adding LDA and getting the two ester pieces by breaking apart the bond between the alpha and beta carbons, making sure both of those are esters and adding them together. Make sure the first step is LDA, last step is H3O+ in these crossed Claisen condensations. Notice that in these other examples, in like the previous exercise we didn't use LDA because we were just using multiple versions of the same molecule. So we just chose the base based on what the alkoxy group of the ester was. But with these crossed groups, where you have two different groups, you use LDA, your second ester, and then hydronium. And that is some practice with creating beta-keto esters, thinking about the synthesis you need to create them retrosynthetically, given the beta-keto ester, thinking of the reagents you would need to make it.